Welcome to this talk on mapping beat precision in acoustic signals in the vocal learning harbor seal Foca Vitolina. My name is Lara Burchardt and I did this work together with Reus and Andrea Ravignani. We like to thank the DAAD for my funding and Silvia Leonetti and the Sealcenter Pieterburen. Now, what is beat precision and why do we want to analyze it? By beat precision, we want to quantify how well a certain behavior, in this case acoustic communication signals, follow an expected rhythmic time series. And then the question is whether we can find patterns in that beat precision. For example, is that connected to different species or individuals? Is this depending on the hierarchical status of an individual, or is it connected to the context, the age, arousal status, cognitive capacities, or production mechanisms? And if so, what does that tell us about the evolutionary drivers for rhythmic communication? While this project focuses on acoustic signals, generally the analysis or the concept of beat precision can be used for any time series of behaviors. Let me illustrate how we calculate beat precision. We use the parameter of the universal goodness of fit value that I developed. And please look at the example on the top of this slide. We have in solid bars sound elements and in dashed lines theoretical beats that we now want to check and match to one another to see how well the sound elements follow this theoretical beat to end up with a value describing the beat precision. We know the maximum possible deviation that any of these elements could have to the next beat, which is half the beat length, and we know the actual deviation any element has to the next closest beat. Setting those two into relation with one another will give us, the UGOF will give us a value indicating beat precision. If it is 0 or very, very low, that means the produced sound elements and the expected events match very well. If it gets higher, there is a mismatch. It's very important how we calculate those theoretical beats. In this study, we use two approaches, two rhythm analysis methods. First, the IOI analysis or IOI approach, and second, Fourier analysis. But we could also use any other kind of expected time series. For example, we could use a temporal template from a tutor or an interactive partner as theoretical beats as well. This kind of analysis can not only be used on acoustic communication signals, but for example also on heartbeats or locomotion and gestures, where we might also have a very good picture of what the theoretical temporal pattern should look like. So far, the dataset consists of 180 sequences of spontaneous pup vocalizations from a total of 10 rescued seal pups, 5 males and 5 females. Pups were between the ages of 6 and 22 days at recording. They're held in pairs, and only sequences are used where the respective partner was quiet. Now, how did we define a sequence, as this has a strong influence on the results? For vocalizations to be considered a vocalization sequence, it had to be at least 4 elements separated by IOIs, so inter-onset intervals shorter than the median IOI produced by that individual in the whole recording day. This is illustrated in the figure on the bottom of this slide. Showing you the preliminary results of this, we see a lot of variability, and we do see that variability between individuals, within individuals, and very interestingly between sexes. Now, the individuals here are on the x-axis, beat precision is on the y-axis. The first 5 individuals are males, the second 5 individuals are females. And we do see that both males and females, at least some of them, are able to produce very precise rhythms indicated by the very low beat precision values. And generally, with that data set, it seems that females tend to be a little more precise than males. The interesting question now is, what explains those differences? Are there possible biases in the data set that could explain the pattern? Can we correlate this to specific behaviors that pups were uttering while emitting those vocalization sequences? Is it connected to the age they produced it, and is it somehow connected to learning, as this is a vocal learning species? And more generally speaking, can we find the same pattern in a different year and in a different cohort? And why and how is this biologically relevant? So while we do see differences, it's still very open why we see those. Thank you very much for your attention. Stay tuned for updates.